Hello students, in this video we'll see how to use reduction of order to solve linear systems where there's a repeated eigenvalue. To solve linear ODE systems with repeated eigenvalues, use reduction of order. So let's see an example of this. Let's solve x prime of t is the matrix 4, 1, negative 4, 8, x of t. So to solve this system, we'll find the eigenvalues of this matrix. So to find the eigenvalues, we'll compute the characteristic equation, determinant of 4 minus lambda, 1, negative 4, and 8 minus lambda is equal to 0. So if we simplify this, we will have lambda minus 4, lambda minus 8, plus 4 equals 0. So, simplifying this further, we will have lambda squared. A negative 4 and a negative 8 is a negative 12 lambda. And then I will have a 32 and a 4. 32 and 4 is 36, equals 0. And this quantity over here is a perfect square. This quantity over here is lambda minus 6, quantity squared equals 0. So we have that lambda is equal to 6. And that is our repeated eigenvalue. So we will use reduction of order. We will seek a solution of the form x of t, which is c1 of t, c2 of t, times e to the 6t, since e to the 6t is the eigenvalue we found. We found the eigenvalue of 6. So now we plug back in and check. So I'll first do the derivative of this. The derivative of x of t will be 6 c1 c2 e to the 6t. That's the derivative of e to the 6t, plus c1 prime c2 prime e to the 6t. That's the derivative of the vector. That is the left-hand side of the equation. Now we'll find the right-hand side of the equation. The right-hand side of the equation will be our matrix 4, 1, negative 4, 8, c1, c2, e to the 6t, which when we simplify will turn into a 4c1 plus c2, and then a negative 4c1 plus 8c2. Times e to the 6t. Now, these expressions must be equal. Every term on the right-hand side and every term on the left-hand side is a factor of e to the 6t. So all those e to the 6t's will cancel out, and we'll get the following system. We will have that 6c1 plus c1 prime is equal to 4c1 plus c2, and 6c2 plus c2 prime will be equal to negative 4c1 plus 8c2. Simplifying this, the first equation will become c1 prime will be equal to negative 2c1 plus c2. c2 prime will be equal to negative 4c1, and then a 6c2 minus 8c2 is plus 2c2. From this, I can notice that if I multiply c1 prime by 2, I'll have c2. This tells me that 2c1 prime will be equal to c2 prime, which is equivalent to 2c1 prime minus c2 prime equals 0. If that is the case, it must be true that 2c1 minus c2 is equal to a constant a. So a here is a constant. Now, if that is the case, then I will have from the first equation that c1 prime is negative 2c1 plus c2, so c1 prime will be negative a, which tells me that c1 of t is negative a t plus b. But now I know that c1 is negative at plus b. I can take that and plug it into my equation over here and conclude that c2 will be 2c1 minus a. And 2c1 minus a will be 2 times negative at plus b. That's my c1 minus a. So my c2 of t will be equal to negative 2at plus 2b minus a. Now I have found c1 and c2, so this is my c1 right over here. And this over here is my c2. So I go back to my formulation of x of t. I fill in c1 of t over here, and I fill in c2 of t over here, and I have a solution now that depends on the constants a and constants b, so I have a general solution to the ODE system by reducing the order. Thank you very much.